So question, how many subintervals, in other words, what's the value then, guarantees me that Simpson's rule within subdivisions approximates this interval to be within, oh, that many units? And here too, maybe my example is not very good because we can evaluate the interval, get the exact value, but humor me. It's just a process I want to show you. Just save time with the using a calculator on the videos. So there's something I cannot prove to you at this stage of the game. Now, I don't like teaching anything in mathematics without being able to explain why it is. That's the uniqueness of the discipline of mathematics. Here's an example where we're going to have to wait for more sophisticated mathematics to prove this, but here we go. It is the case that if you're using something to approximate this integral right here, then the error in using Simpson's rule within subdivisions in absolute values is bounded above by this expression, where k is nothing more than a numerical value that's an upper bound for the absolute value of the not nth but fourth derivative for f with respect to x over the interval from a to b. Now, because I can't derive this formula out of thin air, if you need this in an exam or quiz situation, I'll give it to you. I don't give you things like this when you can derive them on yourself. But since you can't derive this without more advanced mathematics, I'll give it to you. I may not tell you when and where to, or how to use it, but I'll put it, say, on the top of an exam or a quiz if you need it, so that when you do need it, you've got it there. You don't have to commit it to memory. All right, having said that, let me go back to my actual question, which is, how many subdivisions do I need in order to allow Simpson's rule to approximate this definite interval to within this number of units? Well, the error in using Simpson's rule within subdivisions and absolute values is bounded above by this. Was that a k times a b minus a to the fourth power, to the fifth power? But b minus a is 3 minus 1, which is 2. All divided by 180 times n to the fourth power, but I don't know what n is. I'm trying to find it. Now, if this is an upper bound for the error, but I want the error to be less than that, then I think it suggests that k times 2 to the fifth all over 180 times n to the fourth should be bounded above by whatever that value is. I have no idea what it is. I made it up out of thin air when I wrote it in the board. Is it tens, hundreds, thousands, 10,000, 100,000s? So 1 over 100,000. Now I'm going to solve this equation for n. Whoops, shoot, I can't. I can't solve for n because look what I'm erasing. So I can write it more clean so you see it. It's a k. And so I can't solve for n unless I know what k is. So I guess what I'm really saying is I need to take a break. And taking a break, let's find that value for k. So everybody, here I go. Now, k was an upper bound for the fourth derivative in absolute values of x over the interval from 1 to 3. Now, here's my function f. Here is derivatives. Now you take a peek at this function. It's already positive, so I'm not going to worry about absolute values. But certainly in the right-hand plane, that's definitely a decreasing function, just like your hyperbola y equals 1 over x, just with more extreme curvature. And so because this function is strictly decreasing over the interval from 1 to 3, don't you think it's going to max out in absolute values at the left endpoint? And so I think I'm going to choose k to be equal to the f fourth derivative evaluate at the, I was it correctly, left endpoint, which was positive 1. But that's just going to be 360. So I don't know if I made that very clear. In absolute values, this is what it is. Over there from 1 to 3, I'm in the right-hand plane. Clearly, this behaves much like 1 over x, your hyperbola, just more extremist behavior. And since it's a strictly decreasing function, I think the maximum value is going to be at the left endpoint, which is +1. And the fourth order derivative, e value at +1, is that number there. I've got my k. So k is equal to 360. I need to erase. Now, in rewriting that relationship right there, where k is equal to 360, I can solve for n. Well, I misspoke. I can solve for n to the fourth. Now, I apologize, excuse me, for not answering this question before I created this video. So if you'll allow me to come to my calculator, I have no idea what this is. Let me compute this numerically. Because once I plug that k value in, I have one inequality involving n. I can solve for that inequality. Well, I can solve for n to the fourth in that inequality. N to the fourth ends up being this. So 32, 360. Oh, I have an approximation symbol. It's exact. It's this. Oh no. I don't know if I have any reading glasses. Shoot, I can't read this. Darn it. Sorry. Dealing with old people. So 1, 2, 3, 4, 5 zeros. My goodness. Now I'm taking the fourth root. I'm coming with approximately 50.3. But everybody, it's not really going to work, is it? Because technically speaking, n is how many subdivisions I have. I can't have approximately 50.3 subdivisions. It has to be a natural number. So I'll choose n to be at least 51. I think. Actually, that's not going to work. Recall that with Simpson's rule, I have to have an even number of subdivisions. So technically speaking, I've got to go up to I have to go all the way up to 52 subdivisions of the interval from 1 to 3 so that Simpson's rule will approximate that interval over there, accurate to within this value right here. That's a good question. Bit of arithmetic involved, but it's a good question. Do you mind if I take that back? I don't think it was a very good question, because technically speaking, I erased it, but the fourth derivative function that gave me the value of k was monotonic. It was strictly decreasing. What if it's not strictly decreasing? How do you determine the maximum value for the fourth order derivative, evaluated x in absolute values over the interval from a to b? Let's do that next. Let's make this more sophisticated. Interesting.